Okay, in that case, welcome to the November edition of Haskell. It's been a long time. We apologize, it's very difficult to find speakers, so big thanks to Farhad and Marc for volunteering. Today's topic is you're all Haskell users or Haskell user aspirants or ex-Haskell users, so surely you know what Hoogle is. So Farhad and Marc have decided that it would be nice if people who write other languages could also have a Hoogle. And they're going to present today type-driven search for languages other than Haskell. Give it up for Farhad and Marc.
Thank you very much, Kazim. Just give me a minute. I think there. That should be much better. Okay, cool. Welcome everyone. Nice to see everyone here again live for the Haskellers meetup. Really happy to be here. This is work that both of us have done together. Marc is or was a master's student at the OST, and this is something that I'll tell you the story about this a little bit later. Yeah. This is I'm Farhad. This is Marc. This is part of Marc's master's thesis, which he finished. I think it was last year, right, at the OST.
Yes.
Yeah. Cool. So for those of you who are new here, so the OST is a university not far on the other side of the lake from here. It teaches many things, among others also computer science, and it's also the place where we have ZuriHack every year, so I guess many of you already know that. But let me just have a show of hands. How many of you have used Hoogle? Oh wow, everyone, so I don't have to explain what that is. That's nice. So how did this whole thing start? So actually, Marc was doing his master's thesis, and he actually had a different topic, right? You had something totally different, and it was doing something in Java, and his first one was doing something in Haskell, and then we were just in my office one day, and he was doing something, and then we were like, oh, what is that function? And then Marc said, yeah, it would be really cool if we had something like Hoogle for Java, and since the topic was anyway not going very far, I said, hey, would you like to just change your topic to Hoogle for Java? And I meant it as a joke, right? I said that, yeah, you can fail this one, and then you can try it again, and we can do this. And he said, yeah, let's do it. And so that's what we ended up doing. And so, yeah, I'm really happy that Marc took the risk, and yeah, now we have something like this. By the way, we've presented this at the Types workshop for ICFP a few months ago in Milan. So this is the same work that we presented there as well. Yeah, so a little bit of motivation. Yeah, many people do API search. Yeah, and what do most people who do API search in mainstream languages do? Well, they open Google. I mean, now they open ChatGPT, I guess. But at that time, like 6 months ago, they used to open up Google and they say, "Oh, I need something to get the length of a string," and they would find stuff, right? So currently, API search is basically web search. Yeah, it's text-based. There's no real intelligence inside it. I mean, also with ChatGPT, there's no real intelligence behind it, by the way. So what we actually want is not text-based search. We want actually search based on some specification. Yeah, and for those of us who are aware of functional programming and types, we know that types are some form of specification. It's a formal specification. So this idea of having a type-based API search is something, it's quite near to us. And it's not something new either, right? I mean, we've had Hoogle for a very long time. But you know, OO people also deserve nice things. And so we're trying to sort of extend this a little bit, yeah? So it's only possible, this idea of type-based search is only possible for a select few. We know Hoogle, and we're going to take a look at a little running example. For those of you who have not used Hoogle today, at least, let me just give you a little reminder what it looks like and what it feels like. So we have, this is Hoogle, and let's say I want a sorry?
String to byte string.
String to byte? No. Let's do something a little bit more functional. Let's say I want something that takes a list, takes something that chooses elements from a list and gives me the list that satisfies it. So the type of that will be something like a list arrow a arrow bool, for example, and it gives me back a list. So, and it gets it, it's filter, right? But there are many more, take while, drop while, and so on. Yeah. Okay, so this is how Hoogle works. This is its user interface. And now let's take a look there. Yeah. Okay, so now this idea was not very new. It's also not very new for other OO type languages. So in 2016, another master student of mine also had this idea of doing this for Scala. So he did this with a tool called Scaps that was also a prototype. But at that time, he only used also these text-based search vector type methods. Yeah, and yeah, it was there as well. And yeah, it was presented in Uppsala at Splash at that time. Yeah, and it was okay, but there was still an itch there, right? And it somehow, we claimed that it was language agnostic, but when Marc tried to extend it, we found out that not really, and so we said, hey, let's do something else. And so now we came up with something else. We have this typesearch.dev. This is the related paper. In case you're interested in knowing the details, it's here, right? And let's do the same thing there. Let's just do a little demo of this as well. Let's do the same thing here. Here we've already have some of these already. So this would be, at least for us, it would be a stream of A's, A arrow bool, and a stream of A's again. And we'll do a bit of search, and we'll see, okay, there's drop while, there's filter, and so on. So yeah, so it's pretty much a similar interface, similar things come out of it, and yeah, it works. So now, yeah, so what makes this approach different from what we did before? This is, of course, this is targeted at mainstream OO languages, whereas Hoogle is something that's only there for functional languages with parametric polymorphism. Yeah? And this has subtype polymorphism as well. So this is, people always thought that, of course, theoretically, the decidability falls. And so people always are a bit careful about mixing these two types of polymorphism in the same language. But it turns out that, at least for type search, it doesn't really make that much of a difference. So something funny that we found out. Then something was, which was a bit, I don't know, we started out with this very search-based approach to this, just like how a web search would work. And then we always thought that, hey, we could do better. This is too special. We could make this even more general. And this idea of the Curry-Howard correspondence came there. And we were thinking that, hey, could we maybe make something that's so general using type theory, yeah? And then we could maybe have a proof search, which would then become type search for us. And so we tried to make this as generic as possible. So instead of going in the ad hoc way, like most search tools go, we went in the more generic way. So we have a sort of like a generic language which has these two types of polymorphism inside, actually even ad hoc polymorphism at the end. So all these three types of polymorphism there, and we tried to map that to concrete languages. And when we did that, we saw that when we moved from the ad hoc world to the more general world, we saw that we could solve a lot more different types of problems. And when we do type search, we were surprised at the things we got. For example, we were not only able to get the single functions that matched our search, we could even generate proofs that combine programs together to get what we want. So for example, I could say, oh, well, I need a function with this query, but if our search was smart enough and fast enough, which we still have to work on, then we could even get small mini snippets of programs that actually did this. So yeah, surprising things came out when we moved from the ad hoc to the general world. Yeah, so we found out that type search is proof search, actually. So we could also use provers to do this, which we haven't till now. And we also found out that code synthesis is something that's also possible, not just one-shot searching, but also synthesis of pieces of code. Yeah.
So what the search engine does there overlaps with the type inference that the compiler does. Yeah, I mean, Java's type inference, for example, isn't very sophisticated. But at work I use Scala and I use Haskell too, and there's sophisticated. So I'm wondering whether there's overlap.
So
in a way, when you write code, the compiler tries to find the interface or whatever that matches that.
Yeah. So the question is that, is there some overlap in the techniques that the compiler uses for type matching in the technique that we use right now?
Yeah.
I'm not aware of what the Java compiler does for this. I need to take a look at it.
In Java, I think the type inference is so there's so little of it that it's probably not a good example. But if you, let's say you had
Scala?
Hoogle for Scala, which is about halfway between Java and Haskell.
Yeah.
There's more sophisticated type inference going on, and I wonder whether there's overlap between what the search engine does and what the compiler does.
Yeah, I wouldn't be aware of that. Sorry. Sorry, maybe I can take a look at that later. Cool, thanks. Yeah, so so this was like the broad overview of what we did, and now Marc is going to tell you some things about the particularities of how we got this to work. There.
Yes. Okay, thank you for the introduction, Farhad. So first I'm just going to go over the general overview of the concept of how these pieces that Farhad described fit together. So at first we start with the API source. API source is some kind of library. It has some source code. It's ultimately what we then want to search through. But as we start, it's somehow in source form or maybe in a compiled form. We then have a source extraction module, which takes these sources as an input and parses them, extracts the relevant information that we then need for performing the search on it, and puts all that information into a search database. All of this can be done beforehand. This is all just a pre-processing step, so this doesn't have to be done at the time that you issue the query. When we actually run a query, we then perform this proof search on the search database, which I will then explain in shortly. Out of this proof search, we get a bunch of proof trees. And these proof trees are then ranked amongst each other. It's basically like how any search engine ultimately needs to rank the various search results by relevance. And then we can display these ranked proof trees as search results. So the green boxes are the search implementation. This is all of this type search as proof search concept. This is designed modularly, so you could, in theory, switch this out with a different kind of search, which is also available on the type search. There is a legacy type search which uses a different approach, which was basically an adaptation of SCAPS. So you can kind of compare the two approaches if you like. Now the interesting part is that only the two first boxes are actually specific to the source language that you want to query. After that, part of the source extraction is to transform the extracted information into a general data model which is as generic as possible across all languages that we want to support, so that in the end, when you query and the query language itself is also language agnostic, then the search just doesn't care about what language you're actually searching through, because all is transformed into this general model. And only at the very end, we then know, okay, you actually wanted to search through Java, so we'll display it as Java code. So an example of this source extraction, what kind of information do we extract? We'll have some examples here. The first example is a simple toString function on the integer class. And if we extract that, it's represented very Haskell-esque. We have the label integer to a string, and then the type of that function takes an integer to a string. And then we can see a second example, string value of integer. This is a static function on the string class. And now we can see that when we extract this, it has the exact same type signature. It takes an integer and gives you a string, but has a different label. So we can already see that, okay, if I'm going to search integer to string, it's probably going to find these two functions. A bit more of an interesting example with some generics. These are then just represented as you would know it from Haskell with a for all E, and then have the E as the parameter in the type. This is an overview of the proof rules that we need to perform the proof search and build the proofs. I'm not going to go into all of these proof rules right now. You can see on the right side is an example of what such a proof looks like. What's interesting to see is that we only need these 6 proof rules to perform all of the search, including all of the various kinds of polymorphism. We'll see an example of such a proof then step by step on the next couple slides. But we're going to start first with the query, because that's the first thing that as a user that you input. So this is the example that Farhad showed before in the demo. So we write stream A and then A arrow boolean, and then we want another stream A back. And when we transform this into our proof sequence, which we then label with a G for goal, just because we want every type to have a label, we can see the generic is simply transformed into a for all, and then the types are very straightforwardly just converted into this syntax. So before we actually start with the proof search, we want to normalize the goal, bring it into a kind of form that we can then easily work with, that also reduces the amount of proof rules that we later need and makes everything more streamlined. And the first thing that we want to do is we want to eliminate the quantifiers. So to eliminate this for all, we introduce a new type. We just invent a type, in this case f, and then we instantiate this type with f. Then the next step, now that we don't have any quantifiers anymore, we try to eliminate the arrows. And for that, we can introduce, we can move it kind of to the left side and introduce new terms in our proof context. And then we can build this new term on the right side where these new terms are just applied, and that then reduces the type that we have on the right side. So by introducing this G1 and G2, which are basically, you can think of like the function arguments to this function, we then end up with only the return type of the function. So now we have arrived at the, what we call the normal form of our goal. So we can now try to search for actual proofs. In this example, I'm going to limit myself to a single actual search term that we have in the proof context, which is conveniently the filter that we actually want to find, just to keep it a bit simple. So again, this filter is parameterized with an for all t, and we're going to instantiate this t now with f. F is again the type that we just invented previously. Now that we have this for all eliminated, we can start kind of this resolution process where we start applying terms to the function to reduce the type down. And again, we can apply the G1 and G2 because we can see, this stream f, we can apply G1, it's the same type. And then G2, we can apply predicate f. And now, like those that have been paying attention, you'll notice that G2 is not actually predicate f. It's f arrow boolean. So why are we allowed to put G2 there? This is because the concept that we, called type mapping that we have. And type mapping is a process of the source extraction, which is then language specific, which extracts information about types that can be considered equivalent in this language. So for example, in Java, there are these functional interfaces which quite freely allow you to convert types between these interfaces and lambdas or these types. So that's why at least for Java, this predicate of any type is basically equivalent to this type arrow boolean. And with this knowledge, we are then allowed to use G2 in this place where otherwise we would need this predicate. So now for the final step, we have found or constructed a term in our proof context which has the exact same type as what we have on the right side on our goal. So we are finished with a proof search. We have found a proof, which then means, well, we can unify on our variable G that we introduced all the way at the beginning. And we find, okay, G must be filter. And that gives us the information that, okay, we can now use filter as a search result. Yeah, again, this is the example that Farhad showed, just highlighting again that we have this query that we just walked through, and then filter as one of the results. There are, of course, other results. In this case, the reason why filter is shown as a second position is because it has the exact same ranking as drop while, because it's the exact same signature. It's just lower alphabetically. That's just the tiebreaker we decided to use. Right?
Yeah. Thanks, Marc. Yeah, so as you see, this is still work in progress. So some of the things that we'd like to do in the future would be to make use of existing proof search algorithms. At the moment, we have something quite, at least for the proof search, something quite heuristic, ad hoc, right? It seems to work nicely for single-step proofs. But yeah, this is something that we still haven't taken a detailed look at. Also, the idea that we could use this for code synthesis. At the moment, we only get functions that exactly, so one function call that matches this type signature. But of course, I mean, since this is a proof, you can have a more complicated proof, so not proof that has more than just one term inside it. And this would correspond to code synthesis, where it would basically do all the combinatorics for you, and you would get like a small snippet, like a function call that it has exactly this type. Of course, this makes the proof search even more, proof search space even more exhaustive, which is something that we haven't taken a look at because of that, yeah. Then, of course, we said that this is a generic, and this would work for any typed language which has ad hoc polymorphism, subtype polymorphism, and parametric polymorphism, just like Java, for example. But we haven't implemented it for any other language apart from Java. So yeah, this is something that we should also do at some point. Yeah, good. Sorry.
There is an open pull request from another student for Go.
Ah, yes, of course.
Yeah.
He sent something.
Yeah.
Wow, crazy. Okay.
Yeah, I've already reviewed it. It's just yeah, it's not quite ready for merge yet, but it's getting there.
Wow. Okay. Cool. Nice. Okay. Yeah. So 2 languages. Okay. I should take that away from my slide then. Good. Yeah. Conclusion. Then yeah. So type-directed API search for mainstream languages is possible, right? So we could do something like Hoogle for languages which have subtypes as well, which is something we didn't know when we started this work. Yeah. And what's great is that all this work can be done in a nice systematic and language-independent way. So we don't have to really, we can do this ad hoc business just at the top of the slide, like how Marc said, and the rest of it can remain the same, which is quite great. Yeah, and try it out in case you have anything. Thank you very much. Yes.
Can you show an example that involves subtyping?
Subtyping.
Yes.
Yes.
Subclasses.
Mm-hmm. Subclasses. Do we have one, or in the paper?
In the paper, there's definitely an example.
Mm-hmm. Let me try to find it then.
Yeah, I mean, should be able. You could search, for example, array list.
Okay.
arrow int.
Okay.
And it will find list size.
Aha. Oh, you mean we can do it right now?
Yeah,
let's do it now. Okay, cool. Let's do that. I thought you wanted to see a proof.
Well, okay, a proof would be a bit more.
Yeah. Is there one of these standard ones? Yeah.
List. Well, anything, and then arrow int. That should hopefully. Well, okay. First of all, I guess it finds all kinds of things like hash code, but there is like this get length down here. How do I? Okay, this way. And then, so yeah, it finds array list size. I guess array list redefines size in that case, so it's not really that much of a helpful example. But yeah. I guess the best example in this case would just be like object hash code, and it's not the most exciting example.
Alex was next.
Yes.
Yeah.
Could this be useful for languages with gradual typing or no explicit typing, such as, let's say, Python, TypeScript, JavaScript, mix?
Yeah. So one of the goals was that I also wanted to do it for TypeScript. Didn't get to that, unfortunately. It needs type information to work. If it's only like partial type information, it depends what exactly you do with that in the source extraction. So one possibility would be that just any like untyped variable, you just assume that it's like the object or something like that. And I mean, Java has a lot of APIs where it's just object something, and then yeah, you probably have to handle it something like that. But if you like enrich that information or invent that information in source extraction, then the search wouldn't really care.
Yeah, I mean, the most trivial way to do this would be to just say, since this is type theory, you could just say that this exists a T such that, but then it'll have so many hits that it'll become unusable. Yeah, but you can, since this is full type theory, you can do anything what you can do in logic. So yeah.
I'm wondering how much of the kind of the mapping from the signature to the actual functions you have can be pre-computed. Can you do that, especially if you don't have a huge source set? Can you just pre-compute all of that, or a large amount of it, and then the ranking maybe can just be done live? I don't know.
So do you mean like so that the bunch of searches would just be lookups, like
all of the valid searches you've already figured out?
I mean, in theory, it's possible. It's just didn't look into that, to be honest. Maybe you could do it for like two parameter searches or stuff like that. But in the end, that would just be performance optimizations, of course, which are interesting. But that's not really the focus that we had in this work. It was more like the feasibility.
And it could give you interactive search as well. So as you type, it could be showing you what the available remaining.
Yes. If it were fast enough, then yes.
What are the source sets exactly? So for Java, it's probably the standard library. How about the extended ecosystem?
So it will be this link here. You can see it says there searches currently through 50 modules. No, it's like a pop-up. You just have to click on it. Where it then lists what it all searches through. Currently, it's just a list that I just hard-coded in there. It's not something that's configurable yet, really. So there's the JDK, and then there's just a couple, like 5 or 6 libraries that I just chose that were easy to add just to show that it can search through more. And you can also, similar as Hoogle, you can specify only search through this module, do not search in this module. You can do all of that as well.
But could you, for example, index all of Maven Central?
So indexing all of Maven Central was like one of the stretch goals, let's say, or at least like the most popular 100 or something like that. Didn't really get to that yet. These modules are downloaded from Maven Central, but of course it's still a very small size.
The funny thing here is that when you do, it's like a different goal, right? When you do, when you search for a proof, right? You're happy when you just get one. Over here, the problem is you get so many valid proofs that you have to somehow choose what to display. That is the bigger problem. So the more things you have, the more proofs you'll find, and then to rank them is a pain. That's the problem. So we need to find some way of doing this lazily so that we can rank them in a nice way. Okay, we can come up with them in the way that you want to see them. Yeah.
But is there perhaps a heuristic that could help you rank? So perhaps in your current set of modules, all the results are equally ranked. But is there some kind of environment heuristic, perhaps by the types that you're using, that would be better with more libraries having? Or would this have to be a human-provided heuristic?
I mean, it's definitely something to investigate. So, for example, you could just start by searching through only the most popular libraries, and only if you don't find anything there, start searching through more uncommon libraries, stuff like that. But yeah, those are definitely considerations that we haven't accounted for yet. Would be interesting to pursue.
At this point, we were just happy that it works.
Yeah.
So, Rafael, you had a question as well. Is that?
Yeah, if you change the A to something more specific, will it then still find the same results?
This one?
Yeah, the generic. So if it's like array list of string, for example. Yeah, so you see it still finds hash code. But I mean, it finds anything arrow int will find hash code. So, it's roughly, so it still finds size, for example. So it knows that a string could be the instantiation of the generic, and then it returns the search result.
But it will rank string higher than generic.
Yes, it will.
I was just playing with both versions of TypeSearch because I was curious.
So we have to repeat the question. Yeah.
I noticed that the new version seems to have severe trouble with map-like functions. Given you're nodding, it seems like it's something you know about. Do you have a hunch why that is?
Okay, so the question is why the newer version, the proof search-based version, is worse at finding map type functions than the legacy version. So I assume you've probably been searching with list and then something like map or filter.
Basically, I tried with several generic container types and just a second argument that's a unary function that transforms some type A to some type B and returns that initial container with one type parameter flipped accordingly, right? So
yes, so the problem there is a bit how Java treats collections. Basically, Java doesn't actually have a map function for generic collections. It only has map for stream. And so what the search would have to figure out is that I first have to convert my collection to a stream, then I can map it, and then I need to convert it back to a list or whatever container you were using, which it could do with the code synthesis approach, but it's currently just still way too slow. So we just don't do it. The version that you can see just doesn't do that.
Although the weird thing is that apparently the Guava library that you include in the source set does have these transform functions. And the old TypeSearch finds them and displays them on top, and the new TypeSearch just doesn't, so maybe.
Okay, so yeah, I would have to look into that in detail. It's hard to tell what exactly it's doing under the hood and why.
One report.
Yeah. There is a function, so you can see on the right side, there's thumbs up, thumbs down. So if you don't like the search result, you can thumbs down it, write a comment, and then we'll get the feedback.
Cool. So Hans-Peter, next.
Have you ever looked at the search functions that lean for offers? I'm not a specialist, I just did some looked a little bit, and you really can look for proofs of theorems, but theorems might be functions, in the programming sense.
Yes, so the question was, have we looked at the proof search for lean? Yeah, so actually the external examiner for this thesis was Joachim Breitner, who actually did this work on lean. And so he pointed us also in this. So yeah, we haven't yet looked at that. So we haven't yet taken a look at external proof search scenarios for this. So yeah, that's something we still have to do. But yeah, you're right. This is something that definitely, to reuse these proofs is something that's missing right now, yeah.
I think the purpose is the libraries and the proof libraries are huge.
Yeah.
Over all of what Lean produced.
Yeah.
And it's like with your Java search, it's limited to Lean, but it looks fantastic.
Yeah.
And they combine it now with ChatGPT.
What? Okay.
That you can freeform questions.
Okay.
And it really returns technical stuff.
Okay. Okay.
Just to get ideas.
Yeah. That's a good point. I may have to.
Yeah, we'll have to.
Yeah. You have to be more open-minded to this AI business now. Yeah. Thank you. Thanks, Hans, for your Rafa?
This language agnosticism of the larger part of the system, could this also be used to compare APIs in different languages?
So probably that's not really the question was whether the language agnostic model can be used to compare APIs across languages. Probably it's not really the focus of what we can do here with our search engine, but what you could do, currently not because it only has one language, but you could, for example, issue the same query against different languages and then see what you get. You could even kind of translate code between languages by kind of looking for the function that you know in your language and then take the query for this function and then issue it for another language, and then you get kind of the equivalent function in the other language. So that would be the closest that you currently do. But if you wanted to like compare APIs, like see how they differ, I think it's more to see how they are same than how they are different.
Is there any particular handling of exceptions or?
Yes. Effect systems in
Yeah,
general.
so the question was whether how we handle exceptions in the signature, and the answer is we currently do not handle them or take them into account. That's something that we would have to add to the query language and then into the information. Yes. Yes, John.
What happens if I give one of these search results a thumbs up or a thumbs down?
Your feedback will be.
Question is, what happens to
The question is what happens when you click this thumbs up or thumbs down. Once you fill out this little form, it enters into a database, and then maybe if I have time on a Sunday evening, I'll look into the database and then. Yeah. I mean, yeah, exactly. So we don't have like a sophisticated system yet to handle these feedbacks, but we just wanted to give the possibility to collect this feedback and then maybe like process it when we have time to do so.
Cool. Any other questions? No. Okay, cool. Thank you very much for your interest.
Thank you.